Okay. I have summoned a cat. Cool. Hello. What? No. No. Dude. Okay. So this time we're going to talk about systematic and random error. So a systematic error is one that influences a person's score in the same way at every repeated administration. A random error is one that can be positive or negative for a person, or one that changes randomly by administration. So in our preschool literacy example, as students focus less on the test and more on their surroundings, their scores might involve more guessing, which introduces random error and assumes the guessing is truly random. Now, interestingly, I've seen this in some pilots of early measures, that some students tend to choose the first option when they didn't know the correct response. So this resulted in systematic score changes in their scores based on how often the correct response happened to be first. So, how do we distinguish between systematic and random error? Because it's difficult. Some features of a test or test administration can produce both types of error. So a popular example of systematic versus random error, like we can demonstrate that with a flawed T-floor scale. So revisiting that example, suppose I measured my kids' weight every day for 2 weeks as soon as they got home from school. In this example, I'm gonna use my niece, who's 6. So suppose at the time, I have no idea how much kids weigh. Probably 60 pounds is a bad amount for a 6-year-old. I'm not saying my niece is 60 pounds. Okay, let's use a nephew. Not that I have one. Archie, can I help you? Okay, now. Anyway, okay, so the example I have here is an 11-year-old boy. Because I needed some good examples of weight. But there's no way for me to draw this back to my own life because I have 5 sisters and 2 nieces. And that's it. All right. So, suppose this mysterious 11-year-old boy, on average, across the 2 weeks, weighs 60 pounds. But this varied with a standard deviation of 5 pounds. Why would there be such a large fluctuation? What would cause this mysterious nephew such a large standard deviation, according to that floor scale, to differ from their true weight at a given measurement? What about his clothes? Toys were in his pockets, or how much food he had for lunch? Those are all explanations. All right, so what type of error does the standard deviation not capture? Systematic error doesn't vary from one measurement occasion to the next. So if a scale isn't calibrated correctly, it may systematically over or underestimate one's weight consistently from one measure to the next. And a constant doesn't have any variability. So, only one kind of error is captured in E under classical test theory: random error, a systematic error that occurs consistently across administrations, will become part of true score and will not reduce our estimate of reliability, even though it clearly isn't part of the reliability. Like, it's not, it's error. Okay. Cool. So that's wrapping up. Can I help you? Maybe? I don't know what he wants. Hi. What do you want? Oh. No, you can't move the lights. Please don't move the lights. That makes my editing so much harder. Okay. Cool. So next, I'm going to talk about reliability and unreliability. So I've made another plot here that is really similar to the one we already talked about, where we identified our test score, our true score, and our error score. So this time, I have scores from 2 reading tests. The first form is called X1, and the second form is called X2. And we're going to focus on that overall points in the line and kind of illustrate that a person with a true score on 11 should, in theory, have a true score of 11 on, or not theory, but like based on classical test theory, will have a true score of 11 on test 2. All right, so in this illustration, the solid line represents what we would expect to see for a true score. We don't actually know anyone's true score, even those students who happen to get the exact same score across both tests. The point is, in this figure, are all observed scores. So the students who score the same on both tests indicate more consistent measurement. However, it could be that their true score still differs from the observed score. There is no way to know. To calculate the truth, we would have to administer this test an infinite number of times and take the average, or simply simulate it, as we did way back in a previous video. So now that we have the simulated scores for a new form of the reading test called Y, note that row here is made up reliability, which I've set to 8. We'll explain what that means like soon, I promise. And X is the original reading score. So form Y, which is easier, has a mean of 6 and a standard deviation of 3. Now, the assumptions of classical test theory make it possible to estimate reliability of scores using a sample of individuals. Again, that plot shows the scores of 2 test forms, and the overall scatter of the score from the solid line gives us an idea of the linear relationship between the two. There appears to be a strong positive linear relationship, thus people who tend to score high on one form also expect to form high on the other form. So we can essentially just correlate these two factors. So the correlation coefficient in this data set, we can just calculate as I've hopefully put the R code on the screen, or I've directed us to the R code in the website. And this correlation gives us an estimate of how similar, on average, performances between X1 and X2. Because the correlation is positive and strong for this plot, we would expect a person's score to be pretty similar from one testing occasion to the next. Now, imagine if the scatter plot were instead nearly circular, with no clear trend line from one test to another. The correlation in this case would be near 0. So what would we expect from a performance in this case? Would we expect someone to receive a similar score from one test to the next? Or, on the other hand, imagine a scatter plot that falls perfectly on the line. If you score 10 on one form, you would also score 10 on the other. Correlation in this case would be 1. Would we expect scores to be consistent in this case from one score to the next? Think about it. Okay, so now I've given us enough kind of theory to give us a statistical definition of reliability. So in classical test theory, reliability is defined as the proportion of variability in X that is due to variability in true score T. Now, hopefully I've tidied this up. So essentially it's sigma squared of T divided by sigma squared of X. So note that the true score is assumed to be consistent for a given individual, but not across individuals. So thus reliability is defined in terms of variability in scores for a population of test takers. Why do some individuals get higher scores than others? In part because they actually have higher true scores or higher ability than others, but also in part because of measurement error. So they got lucky. So the reliability coefficient that I've given us here tells how much of our observed score in X is due to true score differences in our test. Cool. So that's wrapping that up. All right. I think I'm going to take a break.